You've seen it happen. A million files, a massive playlist, and it all gets sorted in an instant. How? Well, a lot of the time, the secret sauce is an algorithm called Quicksort. Today, we're going to pull back the curtain and really dig into how this computing powerhouse works its magic.
So let's just frame the problem for a second. Really think about it. You have a million of anything. A million photos on your phone, a million rows in a database. How on earth do you put all of that in order in a split second? That is the exact kind of massive challenge that Quicksort just eats for breakfast.
And sorting isn't some abstract, nerdy thing. It is happening constantly, right under our noses. Every time you scroll your social media feed, every time you search for something online, even just looking at the files on your computer, something is putting all that information in order. It's a universal problem, and it demands a seriously fast solution. Okay, so how does Quicksort get that incredible speed? The secret is, well, it's actually kind of beautiful in its simplicity. It's not about being stronger or faster in a brute force kind of way. It doesn't just charge head-on at one massive tangled mess of a problem. Nope. The real genius here is that it does the exact opposite. It takes that one huge, intimidating problem and just breaks it down into tons and tons of tiny, manageable, much easier to solve little problems. And this whole strategy, it has a name, and it is the key to everything. It's called divide and conquer. And look, this is not just a clever name. It's the entire philosophy, the very soul of the Quicksort algorithm. If you can wrap your head around this one concept, you are well on your way to mastering it. The strategy itself is just so elegant. You take a big challenge, you break it into smaller, neater subproblems, and then you solve those. Now, the key ingredient here is the word recursively. Don't let that term scare you. It's just a fancy way of saying we apply this exact same strategy over and over and over again to each new little piece until the entire job is done. All right, so divide and conquer sounds great in theory, but how does Quicksort actually do the dividing? Well, it has this brilliant little engine at its core, a mechanism called partitioning. This is what makes the whole thing go. To get this partitioning engine started, we first need to pick one element to be our pivot. Just think of it like a stake in the ground, a benchmark. For now, let's keep things super simple. We'll just grab the very last item in our list and call it the pivot. The entire goal now is to rearrange every other item based on a simple question. Are you smaller or larger than this pivot? And that's the whole game right there. We want to shuffle the list so that every number that's smaller than our pivot ends up on its left side, and every number that's larger ends up on its right. The pivot itself, it's going to land smack dab in the middle of those two groups. So how does this shuffling actually happen? Well, it's pretty clever. Imagine we have two pointers. One pointer just marches through the list one item at a time looking at everything. The other pointer acts like a gatekeeper for the small numbers club. Every time our first pointer finds an element that's smaller than the pivot, it signals the gatekeeper who moves over one spot and swaps that small element into the club. Once we've checked everything, we swap the pivot into place right after the last member of the club. And here is the coolest part. This is the real aha moment. After just that one pass, that single pivot element is now in the exact final position it will have in the fully sorted list. It is perfectly placed, and it will never have to move again. It's like we just snapped one piece of a giant jigsaw puzzle perfectly into its final spot. Okay, great. So one element is sorted. Big deal, right? We've still got a ton more to go. But this is where that recursive idea we talked about comes back in a huge way. This is where the cascade really begins. See, by putting that one pivot in its proper place, we've done more than just sort one number. We've perfectly divided our original big problem into two completely independent sublists, the group of smaller numbers to the left and the group of larger numbers to the right. We now have two new, smaller sorting problems to solve. And how do we solve these two new problems? You guessed it, we do the exact same thing. We just run Quicksort on the left section, and then we run it again on the right section. Each of those gets its own pivot, gets partitioned, and gets split into even smaller pieces. This process repeats, breaking the problem down again and again, until every single element has been used as a pivot and is locked in its final sorted place. This all sounds incredibly fast, and on average, it absolutely is. It's called Quicksort for a reason. But And there is a but. Its performance isn't always the same. This leads to a critical question. Is Quicksort always quick? The answer, surprisingly, is no. And it all comes down to how well we choose our pivot. Let's look at the two extremes. In the absolute best case, our pivot happens to be the median value. This splits the list into two perfectly equal halves, which is the most efficient way to divide the problem. But the worst case? Imagine our list is already sorted, and we keep picking the last element as the pivot. We'd always be picking the largest value, creating a totally lopsided split. We barely divided the problem at all, and that forces the algorithm to work much, much harder and slows it to a crawl. Let's put some terms to this. In computer science, we call this time complexity. In the best and average cases, which is what happens most of the time, Quicksort's performance is O of n log n. Now that's just a mathematical way of saying it's incredibly fast and efficient, even with huge lists. But in that worst case scenario, performance drops to O of n squared, which means the time it takes to sort grows exponentially. The good news is that worst case is pretty rare in the real world. So naturally, computer scientists saw this potential weakness and developed clever strategies to avoid this worst-case behavior. They figured out how to make Quicksort robust and reliable out in the wild. So instead of just picking the last element, modern implementations get smart. One simple fix is to pick a random element as the pivot, which makes the worst-case scenario statistically almost impossible. An even better method is median of 3, where you look at 3 random elements and just pick the middle one as your pivot. And for lists with lots of duplicate numbers, there are even more advanced techniques to keep things running fast. So Quicksort is really just this beautiful demonstration of the timeless power of divide and conquer. And that brings us to a final thought. This core strategy is decades old, but its influence is everywhere. From rendering complex graphics in video games to processing massive datasets in parallel, we are constantly solving today's biggest challenges by breaking them into smaller, more manageable pieces.